Orcas can pressure much larger blue whales and dismantle sharks. Yet when an adult sperm whale slips beneath the surface, the chase simply ends. Not because the sperm whale is invincible in a fight, because orcas hit an oxygen and pressure wall while their target keeps going. Hundreds, then thousands of meters down into total darkness, holding its breath far longer than any killer whale can follow. Surface fortress is one defense. The abyss is the other. Orcas can't take both. Here's the physics that rewrites the hunt. To understand why depth is the decisive variable, start with why size is the wrong first answer. A blue whale at full size can weigh approximately 150 metric tons. A large adult male killer whale weighs closer to 10. That is a mass gap no individual orca can bridge on its own. Yet coordinated groups of killer whales have been documented killing blue whales. On the 9th of March 2019, researcher John Totterdell and colleagues documented the first confirmed orca predation on a blue whale in Bremer Canyon off Western Australia. The victim was an apparently healthy adult pygmy blue whale estimated at 60 to 70 feet, roughly 18 to 21 meters long. A second event on the 25th of March 2019 took a blue whale calf in the same area. A third in March 2021 killed a yearling juvenile. Approximately 50 to 75 killer whales accumulated around the feeding events. The 2022 paper documenting these cases was significant precisely because confirmed kills of free-swimming blue whales are rare in the published record. Rare, not impossible. A 2014 study of an injured blue whale sighted off Marissa in southern Sri Lanka at approximately 05 degrees 48 into north, 80 degrees 28 east, described the animal as thin, apparently unable to dive normally, and covered in parallel rake marks consistent with a killer whale attack. The researchers, drawing on prior literature, described blue whales as animals that resort to flight as their main defense and do relatively little to defend themselves against killer whales. Out of more than 150 photo-identified blue whales in their regional catalogue, only 2 showed rake marks of comparable severity. The blue whale's response when orcas arrive is essentially horizontal. It tries to swim fast enough and long enough to outlast the assault. Orcas exploit that geometry. They fan out, harry from multiple angles, prevent rest, and keep forcing movement. If the animal can't run far enough or long enough, it becomes reachable. Coordinated pursuit beats raw size when the prey's only defense is a straight-line sprint. A sperm whale can't win that race at the surface either, but it has access to another axis entirely. An adult male sperm whale can be more than 16 meters long. Its blunt, square head may account for nearly a third of its body length. That head contains the spermaceti organ, a mass of waxy oil linked to buoyancy control during deep dives, and the most powerful biological sound apparatus documented in any living animal. Mature bulls often travel alone or in loose associations across deep, open ocean, far from the nursery groups of females and calves that form the social backbone of the species. Female and immature sperm whales commonly live in cohesive groups of roughly 10 to 40 individuals, moving and acting together. Calves are born and raised within those units. Adult males, at their largest and most powerful, are solitary, which removes one form of protection. There is no ring of companions beside a lone bull when the water breaks with dorsal fins. But solitude does not mean defenselessness. It means the defense is individual and vertical. The sperm whale's ordinary working day already includes dives that would represent extraordinary achievements for most marine mammals.
Stephanie Watwood, Patrick Miller, Mark Johnson, Peter Madsen, and Peter Tyack published a landmark 2006 study using digital acoustic recording tags to monitor 37 individual sperm whales through 198 complete
and partial foraging dives across the Atlantic Ocean, the Gulf of Mexico, and the Ligurian Sea. Their average dive cycle lasted 45 minutes, followed by a surface interval of approximately 9 minutes. Most of the dive was spent actively working. The whales produced regular echolocation clicks for 81% of their time underwater, and they spent more than half of every dive cycle actually detecting and attempting to capture prey. That was routine, not a record attempt, not emergency behavior driven by predation pressure. Feeding. Earlier literature reviewed in that study reported the majority of sperm whale dives lasting 33 to 53 minutes and reaching between 400 and 1,200 meters. NOAA Fisheries describes common hunting behavior as dives of roughly 600 meters lasting approximately 45 minutes. Extreme recorded durations, including a 117-minute dive documented off South Africa in 1969, and older literature citing cases of up to 138 minutes, exist as historical data points that represent rare exceptions, not averages. In the Gulf of California, where sperm whales hunt Humboldt squid in a semi-enclosed sea with maximum depth exceeding 2,000 meters, tagged whales frequently worked shallower prey layers. 91% of deep dives in one study there reached between 100 and 500 meters, with a mean depth of about 418 meters, and roughly 70% lasted between 15 and 35 minutes, averaging 27 minutes. Researchers observed sperm whales surfacing with jumbo squid visible in their jaws on 10 separate occasions. A Japanese study fitted a suction cup time depth recorder to a female sperm whale that stayed attached for 62 hours, recording 74 dives deeper than 100 meters. That animal repeatedly descended 30 to 45 minutes to depths between 400 and 1,200 meters, surfacing for roughly 8 to 10 minutes before going again. This isn't one exceptional animal performing one exceptional feat. It's the species' operating rhythm. In the Mediterranean, researchers found that sperm whales typically began producing foraging buzzes, the rapid click sequences that indicate prey pursuit, approximately 6 to 7 minutes after fluking up and beginning to descend. The whale was already several hundred meters down and still sinking, actively searching on its way to the hunting depth. Each dive was an extended, structured, three-dimensional work session in near total darkness. Now consider what the orca's profile actually looks like in the data. P.J.O. Miller and colleagues used digital acoustic recording tags on 13 mammal-eating killer whales in southeast Alaska, recording 7,608 dives. The calculated aerobic dive limit for adult animals in that dataset came to approximately 9.8 minutes, the estimated point at which aerobic metabolism is exhausted. Adult males and females didn't exceed that limit. Juveniles occasionally did. A separate 2024 study using tags and drone observation documented an adult male killer whale's longest single dive at 8.5 minutes, with most measured dives considerably shorter and shallower. Gregory Shaw, Bradley Hansen, Erin Falcone and colleagues tracked eastern North Pacific offshore killer whales using satellite-linked DART tags in 2022. 2 tags reported detailed diving summaries across 1,110 total dives. One tagged whale had a median dive depth of 41 meters. The other's median depth was 100 meters. Their median dive durations were 3.9 and 4.1 minutes respectively. The deepest single dive in that dataset reached 480 meters. Maximum recorded durations in those 2 animals were 10.1 and 12.3 minutes. These are offshore killer whales, an ecotype that frequents deep water and has been documented taking sharks and other demanding prey. Their median dives sit at 41 meters and 100 meters. Their most common submersions last under 5 minutes. Different orca ecotypes produce different numbers. Transient or mammal-hunting killer whales have recorded maximum depths around 254 meters in some tag datasets. Northern residents have reached approximately 300 meters. Southern residents around 379 meters. The Southern Ocean provides the extreme outlier. One killer whale recorded at 1,087 meters in roughly 11 minutes during toothfish depredation around deep longlines. After that dive, the same animal spent 3.9 to 4.6 hours making repeated shallow excursions, mostly under 100 meters, before its behavior normalized. That record is genuine. It establishes that an orca can physically reach extreme depths. It does not establish that an orca can sustain repeated, extended deep operations as part of a pursuit sequence. The recovery pattern after a single exceptional dive tells its own story. The distinction between a one-time record and a repeatable operational profile is everything in a chase. A sperm whale at 600 meters is operating within the lower end of its routine foraging range. It has descended for roughly 6 minutes. It will remain at or near that depth for another 40 minutes. It's actively hunting, turning, accelerating, managing prey detection across a three-dimensional search volume. These bursts involved rapid acceleration, hard deceleration, and sharp changes in body orientation, all at depths exceeding 400 meters. An orca attempting to pursue at that depth has used a significant portion of its 9.8-minute aerobic window just getting there. The sperm whale may be 200 or 300 meters below the orca's position. The orca must locate a moving target in darkness, attempt engagement, disengage, and return to the surface, all within a closing margin. The sperm whale keeps descending. What makes this physiologically possible in a body that still needs to breathe starts with the rib cage. A sperm whale's ribs are connected to the spine by flexible cartilage. As the animal descends, increasing water pressure compresses the chest cavity. The lungs collapse inward. Air is pushed into regions where gas exchange is reduced or halted. Nitrogen uptake is limited. This isn't a passive surrender to pressure. It's a structural adaptation that allows the thorax to yield rather than resist, eliminating the catastrophic pressure differentials that would cripple a rigid-chested diver at depth. The whale does not rely on that compressed air to survive the dive. Before descent begins, it has preloaded oxygen into two other systems. Hemoglobin in the blood binds oxygen and carries it through circulation. Myoglobin in the muscles binds oxygen at the tissue level, creating reserves available to sustain muscular activity independent of blood-delivered supply. Studies of cetacean diving physiology have identified sperm whale muscle myoglobin content at approximately 74.7 milliliters per kilogram, roughly 9.3 times the concentration found in human muscle tissue. Research on sperm whale oxygen stores has estimated that blood stores alone account for approximately 64% of the total available oxygen at the beginning of a dive. During the descent, the cardiovascular system begins redistributing those reserves. Heart rate slows. Diving mammals universally exhibit bradycardia, a controlled reduction in cardiac output. Blood flow to peripheral tissues is reduced. Oxygen delivery concentrates on the brain, the cardiac muscle itself, and the locomotory muscles actively powering the dive. Precise heart rate measurements for free-diving sperm whales haven't been published at the same resolution achieved for other species. The clearest measured example of this mammalian dive response in a large, free-ranging whale comes from a blue whale instrumented in Monterey Bay by Jeremy Goldbogen and colleagues. During foraging dives to 184 meters, that animal's heart rate ran typically between 4 and 8 beats per minute, with a recorded minimum of 2 beats per minute. At the surface, recovering from those dives, the same heart reached 25 to 37 beats per minute, close to what the researchers calculated as the anatomical maximum for a whale of that mass. Sperm whales dive deeper, longer, and more frequently than that blue whale. Their cardiovascular response is expected to follow the same mammalian pattern, calibrated to a deeper and longer operating envelope. The mechanistic infrastructure is documented: compressible lungs, high oxygen stores, myoglobin-dense muscles, a dive response that reroutes limited oxygen supply to the tissues that can't be temporarily switched off. These systems work together from the first stroke of the fluke downward. The body isn't simply surviving the pressure, It's operating inside it. Now place both animals together inside the event that most directly tests those limits. October 1997. Approximately 130 kilometers off the coast of Central California. Robert Pittman and colleagues observed roughly 35 killer whales attack a group of 9 sperm whales. The orcas had the numbers, the coordination, and a track record of taking large cetaceans. In the Bremer Canyon cases, far fewer animals overwhelmed an adult pygmy blue whale in open water. But sperm whales aren't blue whales. As the orcas closed in, the 9 sperm whales didn't scatter independently. They compressed. Within a short period, the group had arranged itself into a rosette, also called the Marguerite or Daisy formation, after the shape it resembles from above. A rough flower with heads touching at the center and tails radiating outward. The geometry wasn't random. A sperm whale's flukes are triangular, immensely powerful, and driven by tail musculature capable of delivering a strike that could seriously injure or kill a smaller attacker. By facing inward at the vulnerable jaw and eyes and pointing flukes outward, the formation created a structure where every angle of approach exposed an attacker to the most dangerous part of at least one defender. The Pittman paper described the formation with a phrase that is held up across subsequent accounts. The sperm whales appeared largely helpless from a distance, but their collective positioning transformed a group of animals into something much harder to disassemble than 9 individuals separated in open water. The orcas worked the perimeter. They charged repeatedly, probing for gaps, trying to draw individual whales away from the ring. When attackers pulled one animal out of the formation, 1 or 2 of the remaining sperm whales reportedly left the circle to flank the isolated whale and maneuver it back toward the group. Each defensive movement of that kind carried its own cost. Every animal that left the rosette reduced the protective geometry by 1 position. Each companion retrieved was a companion that had briefly exposed itself to attack in open water. The assault lasted approximately 4 hours. 1 sperm whale was killed. The others were seriously injured and may have been mortally wounded by the end of the encounter. Pittman and colleagues didn't treat this as evidence of sperm whale invulnerability. The 1997 California event is essential precisely because it prevents easy mythology in either direction. Orcas can attack sperm whales, sustain pressure for hours, and kill them. The Marguerite formation is a genuine collective defense. It held longer and at greater cost to the attackers than an unprotected animal could have managed. It didn't hold indefinitely against 35 coordinated hunters. What the encounter actually reveals is the logic of 2 separate defenses built for 2 separate situations. When a social group of sperm whales, females, calves, immatures, must remain near the surface because their young can't follow adults on deep feeding dives, the Marguerite formation is the surface answer to a surface threat. The most vulnerable individuals sit at the center. The strongest animals face outward. Every approach costs the attacker something. The 1997 formation held long enough that 35 orcas spent 4 hours killing 1 whale, an energetic and risk outcome that shapes how likely similar attacks are to occur. In northern Norway, researchers documented 4 separate interactions between orca groups and adult male sperm whales during 2008, 2009, 2011, and 2013. A 2025 paper analyzed these encounters. In each case, the males were harassed. The authors considered the possibility that orcas were assessing the males, testing condition, looking for weakness. The adult males involved weren't obviously seriously injured across those documented interactions. The encounters ended without obvious lethal outcomes for the sperm whales. That formation defense, though, requires a group. An adult male traveling alone across deep ocean can't build a ring of outward-facing tails around himself. His defense is more individual and more vertical. What the abyss offers a lone adult is the same thing it offers the species every time a whale flukes up to hunt. An environment where its body is engineered to keep working, and where the cost of sustained pursuit falls differently on the pursuer. The sperm whale's deep domain specialization isn't merely passive endurance. It's active predation in conditions that very few other species can access. Below 400 meters, in water where ambient light has long since vanished, a sperm whale navigates by sound. Those clicks function as long-range biosonar. Watwood and colleagues found that sperm whales descended an average of 392 meters from the start of regular clicking to the first buzz, consistent with the interpretation that regular clicks function as a long-range search system, and buzzes represent the terminal approach phase when a target has been identified at close range. The buzzing itself isn't uniform. The whale isn't executing the same behavior at every depth. It's reading the prey field and switching strategies based on what each layer offers. Squid interaction leaves evidence on the whale's body. Large cephalopods resist capture. Their suckers, reinforced with toothed rings, can leave circular scars on sperm whale skin around the head and rostrum. These marks aren't signs of mythological sea monsters. They are the incidental traces of a predator making contact with prey that fights back. The scars accumulate across decades of dives, a physical ledger of a life spent in darkness at depth. The clicks that help the whale find that prey have attracted a popular extension of the story, that sperm whale sound is powerful enough to stun, injure, or disorient nearby orcas as an acoustic weapon. The measured intensity is genuinely remarkable. The weapon hypothesis, applied to interactions with other large predators, isn't established by the available evidence. The clicks are sophisticated tools. They aren't proven weapons against killer whales, and the sperm whale's survival advantage does not rest on a hypothetical sonic cannon. It rests on dive capacity, oxygen physiology, pressure adaptations, and the economics of pursuit. Predators don't attack every available prey animal in every available condition. Optimal foraging theory describes predator decision-making in terms of energy gained versus energy and injury risk expended. Research on Arctic killer whale predation has noted that smaller, less experienced prey reduces both energetic cost per capture and injury risk to the attacker. The same logic operates at scale.
Attacking a healthy adult sperm whale, an animal with a 50-ton tail, a social unit capable of forming the marguerite geometry, and a deep-water retreat that requires orcas to exceed their aerobic limits to follow, involves a cost-benefit calculation that may not favor attack. The orca's intelligence isn't separate from this calculation. It's the mechanism by which the calculation happens. Orca populations transmit hunting strategies culturally across generations. Some lines of killer whales have learned to beach themselves to take seals from shorelines. Others coordinate in carousel feeding patterns around herring schools. Others work in specific sequences around large baleen whales. Each of those techniques represents an evolved or transmitted efficiency, a way of making dangerous, energy-intensive prey more economically viable. An attack without a clear efficiency path is less likely to be attempted or sustained. A healthy adult sperm whale at the surface, or descending beyond an orca's sustainable pursuit window, offers diminishing returns at increasing cost. The historical record around sperm whales came weighted with a different kind of awe, earned in the worst circumstances. In 1820, the Nantucket whale ship Essex was hunting sperm whales in the Pacific when a bull rammed and sank it. The Essex incident became one of the historical anchors associated with Herman Melville's research as he assembled Moby Dick, though his novel is fiction, not a natural history account, and should be treated as such. What the Essex record establishes is the physical capacity of a large male sperm whale to direct mass and momentum toward a threat. Industrial whaling later demonstrated how thoroughly that power could be overwhelmed by systematic, mechanized hunting. Sperm whales were targeted across centuries for the waxy spermaceti oil filling their heads, valued for oil lamps, lubricants and candles, and for the blubber oil that fueled a global industry. The species remains listed as vulnerable on the IUCN Red List. Modern research measures what whaling destroyed in numbers. Digital acoustic tags and satellite-linked loggers now describe animals living their lives as whaling never could. Before biologging, what happened below the surface was largely inference.
Researchers could time a whale's disappearance and reappearance. They could note blow counts. They could examine the stomach contents of whales killed by whalers and find squid beaks from prey caught at depths no instrument had yet measured. Now, a D-tag records depth at 1 measurement per second, captures 3-dimensional orientation, logs every click and every buzz, and identifies each prey capture attempt with millisecond precision. Shaw and colleagues' satellite tags followed eastern North Pacific offshore killer whales for up to 147 days across their open ocean range. Irvine and colleagues' advanced dive behavior tags stayed attached to sperm whales in the Gulf of California for median tracking durations around 5 days per individual, recording roughly 42 foraging dives per day. Those numbers describe an animal whose entire waking life is structured around a vertical routine, invisible from a vessel on the surface. Sperm whales spend approximately 75% of their time in foraging dive cycles. Flukes up, descent, regular clicking, buzzes at depth, ascent, a surface interval of 8 or 9 minutes, flukes up again. The cycle repeats dozens of times each day. In one California study, the pattern continued without interruption for weeks of continuous tag data across multiple individuals. For orcas, the comparable record shows animals whose routine dive profile sits in the upper tens to low hundreds of meters, whose aerobic window runs to roughly 9.8 minutes before anaerobic costs accumulate, and whose one confirmed extreme dive into the lower end of sperm whale habitat was followed by hours of shallow recovery.
The lockout is the accumulated gap between those two profiles. Not a hard depth ceiling at a specific meter mark. The Southern Ocean record at 1,087 meters proves no such absolute wall exists. But the combined margin of oxygen, time, transit cost, pursuit viability, and recovery demand. Where the sperm whale works every day, the orca visits briefly and recovers slowly. A healthy adult sperm whale has 2 layers of protection, depending on circumstance. In a group, it can contribute to the rosette: heads inward, tails outward, calves and juveniles at the center, adults forming the outer ring, where each approach costs the attacker something physical. That formation has limits, the 1997 California event made explicit. 35 killer whales, 4 hours, and 1 dead sperm whale. Alone, an adult male has no rosette. He has access to the deep, the same deep where he has spent most of his life hunting squid at depths between 400 and 1,200 meters, managing his oxygen stores through bradycardia and myoglobin reserves and compressed ribs, tracking prey in total darkness at burst speeds up to 8 meters per second. The moment he flukes up and begins that 45-minute descent, an orca at the surface faces a specific set of facts. Its typical aerobic window runs to less than 10 minutes. The target is already descending through a depth band where the orca's routine dives don't reach. Pursuit requires spending most of that window in transit, with an uncertain time margin remaining for search and engagement, and the entire window closing before the prey's dive is 1/4 complete. That asymmetry isn't a fight the sperm whale wins by force. It's a physical reality it exploits by living in a realm where the costs of sustained pursuit fall differently. Orcas remain elite apex hunters. Coordinated, intelligent, culturally sophisticated, capable of killing animals far larger than themselves. Sperm whales aren't invulnerable in the wrong circumstances. Compromised, young, isolated at the surface, caught in the wrong configuration. The matchup isn't a cartoon. But apex predation does not mean unrestricted access to every prey species in every habitat and every condition. It means a position near the top of a food web whose structure still includes energy costs, injury risk, and environmental constraints that no predator simply overrides. The sperm whale's deep-diving physiology evolved to exploit the deep ocean as a feeding ground, not as a refuge from orcas. The anti-predator function is a consequence of that specialization, not its cause. The abyss is a working environment, but the consequence is real.
When a sperm whale descends into water where the orca's oxygen stores, aerobic window, and routine dive profile can't sustain the chase, it doesn't defeat the predator. It changes the physics of the encounter until pursuit becomes too expensive to continue. That is why an adult sperm whale can alter the hierarchy without winning the fight. The ocean's most celebrated surface predator isn't built to sustain what the undercredited leviathan does every single day. Subscribe for more stories like this.